think this will still be a good recording, or is it gonna?
Probably. I think it was a little soft before. Maybe, Henning, if you stand in the back, maybe we can just do a quick
Yeah,
check.
yeah, sure.
You guys think
Sound check, 1, 2, 3, 1, 2, 3. No, 0.
it's not audible?
Okay, all right. Let me try the other one then. It's just it's gonna keep falling. Okay, I can try the other one. 3, 1, 2, 3. Is that better? 1, 2, 3. Okay, cool.
Yeah, you can also like rest it on your lapel if easier.
No, no, that should work. So you don't have mandatory attendance. I mean,
No, I figure that
it's a
the
lost cause.
students who are engaged and excited will come, and
Okay, well, that's good
everyone else,
self-selection, and the other ones will be in their bed sipping chocolate.
yeah, they'll be watching it on the course as well. So I can do the intro with
Go
this.
for it. Go for it.
All right, everybody, we're going to get started. So today we have our last class session and also our last guest lecture by Professor Alexandre Bayen. He works on all sorts of exciting things involving how lately machine learning can be used to help us have better traffic and better self-driving vehicles that make traffic better. So hopefully we'll learn a lot about that today.
Thank you. Thank you. So welcome, everybody. It's fun to be here. Full confidence, I finished my slides a few minutes ago, mostly because the data was collected a few days ago. Also, full disclosure, as Sergey mentioned, I am not someone who works in the field of deep reinforcement learning as in an academic field. I'm a consumer of it. I use it, but I don't really contribute to it. I contribute to other things, which you'll see. So this should really be viewed as a lecture to show you what we did with the tools you learn in class rather than advancing the field seen in class. So this is the confluence of three things, two of which have a deep connection to this class. The Circles project, which I will explain in a minute, the Flow framework, which is a deep reinforcement learning framework we produced a few years ago, and the I-24 motion, which is the largest instrumented testbed for freeway in the world that just opened 2 weeks ago and that we happened to use when it opened. So let me start with a general concept on mixed autonomy. What is mixed autonomy? A possible definition for mixed autonomy is the coexistence of vehicles which have a certain degree of automation. It could be, your Tesla or your whatever car has some form of automation, and normal vehicle driven by normal people. So the color code for the rest of the talk is these self-driving vehicles, or these vehicles with some degree of automation, are depicted in red, and the other vehicles are depicted in white. And the whole motivation for the talk, and for those of you who have been at BDD talks or other talks before, you might have seen the first 5 or 10 minutes of this talk, and then after that it'll be really new. But the motivation for this whole work that we started 5 years ago is this graph, which the Deputy Assistant Secretary of Energy at the US Department of Energy, Ruben Sarkar, used to show. It's a back of an envelope computation of the potential energy footprint gains or losses in a future of full automation. And what you see in this graph is that essentially, if you accumulate all the good things that could happen, like car drives more efficiently, and all the bad things that could happen, you send your car to pick up your kids at school, and a bunch of empty cars get stuck on the freeway because there's too many of them. The ranges are essentially from an improvement of 60% to a worsening of 200%. And so the motivation here is really, can we use automation for the greater good? And can we use automation to essentially improve traffic? Now, there's not going to be 100% autonomy for a while. The actual inventor of self-driving vehicles in California, Steve Schladover, who is a Berkeley researcher who put the first self-driving vehicles on the freeways in the 90s, forecasts that it's probably not until 2075 that you will have level 5 autonomy everywhere. That's his forecast. And every year you see on the major newspapers, oh, the self-driving cars are going to be here next year, and it's always next year, and it's been next year for the last 10 years. So in the meantime, you're going to have people like me driving a regular car with some form of autonomy, maybe interacting with other cars driven by people who don't have autonomy. And that's the world in which we'll have to live in. And so what we did and what we are working on is essentially a software-hardware architecture to enable the deployment of machine learning algorithms on board some of the vehicles that have some degree of automation, in the hope that collectively, if we manage to make them collaborate, they can control traffic for the greater good. So right now when you buy a car, and even if it's a self-driving, it doesn't really matter, it doesn't really care whether it's going to improve traffic or not. All it cares is being a good product for you, which means ideally if you could sleep on the wheel the whole way, that's the best product there is. But it doesn't matter to that car what impacts it has on the system, mostly because that car doesn't collaborate with other vehicles. It senses vehicles around itself, it uses that to drive safely, but it doesn't really collaborate with other vehicles with similar features of automation, which is what we are doing here. So essentially, what we're building is a system in which red cars start to talk to each other and start to talk to the back end so that collaboratively they can control traffic and traffic can be improved. And so what you see at the bottom is essentially a system that we built and that we implemented for the first time 2 weeks ago in Nashville, Tennessee at scale. And that's the story I want to say. Now, vehicles collaborate in specific ways. So red vehicles are, quote, automated. That means they can read data from the cloud or through the 5G network or any kind of network, high-level data. And then they have local sensing, radar, LiDAR, and many other things that enables them to avoid collisions. And that means if I'm a red car, I can see and sense cars around me, and for the rest of the talk, they'll be depicted in blue. That means I don't know what's in that car. It could be a person, could be another machine, it could be both. But nevertheless, I can sense my headway, I can sense their speed, I can sense their acceleration, and I can sense maybe a few other things, and I'm going to use that locally to drive better. And then there's other cars in white, the same cars as in the previous ones. Well, these ones, okay, they're here, but I can't sense them, so I don't even know they're there. And if I'm fed information from the cloud, maybe I can be fed global information about their presence, but in general, I just don't know they're there. And so what you learn in this class is essentially to deploy algorithms. I'm sure you've seen that little diagram many times, policies. And where we started with this project is essentially the development of such policies in a very naive manner, because we had never done it for real. And of course, now that we're back from that big test, we look at the world very differently, because everything we thought would work failed. And instead, we did a bunch of other things. And it worked, but it was really nothing like we expected. So what you learn here is fantastic, and we learned it ourselves. And it's just a starting point of a journey where now you have to deal with real problems in the world, and you have to work at it, because it's just not going to work like it works in software. And that's the exciting part. So the story started in 2017, when we figured out, in that little loop here, there's the environment. And the environment is essentially the simulation mechanism that you use to compute a reward. And that reward is what you're improving. And when you've improved the reward, then you are able to run a policy. So around 2015, some tools started to scale. So if you want to simulate traffic, a typical freeway lane in California carries 2,000 vehicles an hour. 5 freeway lanes carry 10,000 vehicles an hour. And if you want to simulate that for many hours, that's a lot of vehicles to simulate. So until 2015, it was very hard to do this in a tractable manner. The tools didn't support it very well architecturally, and the cloud had not penetrated that industry. So believe it or not, people were still running on old stacks, and it didn't scale well. And you can see on this kind of sausage-looking thing here that there are different degrees of precision or accuracy in which you're able to simulate things. That second from the top is what we're interested in here. It's called a micro simulation. It's a simulation tool in which every vehicle is simulated, up to, you could do all the way to inside the hood, so energy models and everything you want. When I started at Berkeley, people told me, don't work on that stuff. It's just science fiction. in 2015, it started to run at scale, and there was enough data to calibrate it, so it started to become interesting. And so that's when we decided to operate at that level, and decided, well, could we have this little environment box be this, which had never really been used at that scale before? So if you've never seen a micro-simulation tool, that's what it looks like. So you can see it simulates everything. You'll see even there's some different vehicles with different masses, so you can see buses or trucks, and each of them have different classes, and all these classes can be modeled. So if you have a super cool sports car, there's a model for it, and if you have a really old bus, there's also a model for it, and if you know the penetration of all of these, then you can simulate things very, very, very accurately. There are a few tools that are commercially available, Vissim and IMSUN. So when we started with IMSUN, which is now owned by Siemens, and then in the meantime, then Sumo came as an open source framework to make this accessible to the community, so then we started also to work with both. And it's kind of the fun part is that when we started, IMSUN did not run on the cloud, which is crazy for 2015, 2016. And we were the first thing they ran on the cloud. So we are the first IMSUN cloud implementation. They built it for us, and of course now it's a product. And so 2 years later is when we released our first framework. It's called Flow. And Flow was historically the first integration on the cloud of micro-simulation tools, Sumo and IMSUN, to run deep reinforcement learning libraries that at the time were also coming online for us. So the convergence of these three things is what enabled what I'm about to show in the next 10 minutes, which then later led to what we did in the last 2 weeks. For this, I would like to take a short deep dive in the history of traffic modeling. This picture is the picture of Bruce Greenshield, and this is the first time, to our knowledge, someone in the history measured a traffic jam. There was a festival in somewhere rural America in the middle, and there was enough people coming to that agricultural festival that they managed to create a traffic jam on a small road, and he recorded it, and he has the first mathematical model known of a traffic jam in the history of traffic jams. 20 years later, hydrodynamicists modeled this as a partial differential equation. It's very famous, and that became the seminal model. Okay, so now fast forward over 50 years, and a Japanese research group did that experiment. They asked drivers to drive at something like 20 miles an hour, or 20 kilometers an hour, I forget, and just hold your distances. So simple, right? It's something like you have a driver license, you should be able to do that. And the amazing thing is that within 30 seconds of starting the experiment, this happens. Like people are just not able to hold their distances. And there's a reason for it, is that humans are very good for certain tasks and very bad for some other tasks. They're very bad for this because there's a delay. Like, okay, you notice the person slows down, so it takes you some time to figure out what to do. Then you slow down, and it takes the car a little bit more to act on it because there's a delay. And then the person behind has now to do the same, more extreme manner because of your delay. And so that's a chain reaction. It's called string stability. And that is the cause of what's called phantom jams, which are things I'm sure you have all experienced on the freeways. You stop, you go, you stop, you go. Even though there's no accidents, there's no nothing. It's just human inefficiency. Or machine inefficiency, because that does not stop with automation. If you put cruise control from different brands together on the road next to each other, this will also happen. So it's not just the human. Like if the automation is poorly designed, it makes it worse. Now fast forward 10 years, and a former UC Berkeley student, Dan Work, and colleagues recreated that experiment in Arizona, but this time they inserted a vehicle in it with some degree of automation. So the vehicle with an arrow here has some level of automation, which for now is not turned on. And when you see the arrow turn red, it will be turned on. And when that happens, it will, in a sense, do what we would like to do, which is to smooth the oscillation, which is what it was designed for. So right now, it's just is driven by a human, and you can see these oscillations happening. They're terrible. Okay, you can see it's like no better than in Japan 10 years prior. And now it turned on, and the algorithm manages to smooth traffic. The algorithm that run in there is an explicit algorithm. It's called the follower stopper. It's not machine learning. It was handcraft designed for it, so you could view this as an expert, if you will. And it was designed to operate at different speeds and so on and so forth. And that's something we'll come back to it, because we'll later use imitation learning to learn it in the later part of the lecture. So this was inspirational, and this was pivotal and transformational, because when they did that, they showed from actual data, looking at the OBD2 ports of the vehicles, that they can improve the fuel consumption by 40%. 40% is crazy, right? Like, so with one self-driving vehicle in these 25 vehicles or 22 vehicles, you can essentially shave the footprint of that instability by a lot. So this was the start of our project, the one that we ran 2 weeks ago. But before we got there, what we wanted to do is see if we can replicate that with machine learning, because we knew that for the real thing, we could not do explicit controllers. It's okay to do a follower stopper in a ring, but if you're going to operate on a real freeway, it's going to be much harder to carve handcrafted algorithms. So then came Kathy Wu, another Berkeley student, who is now a professor at MIT. And so she did this thing, which for you, you'll know exactly why I'm showing you this. So she did the same in simulation. And so you, well, not you, but people who don't take this class should be asking themselves, why is Alex showing a simulation of something that was done in the real world 1 year prior? The reason is because what's implementing here is a reinforcement learning algorithm, but the main difference is that the previous one had a model of all the vehicles in it. This, and that was an explicit algorithm. This one is just deep reinforcement learning, and it's using a simulator as a black box, doesn't know the model, if you will, just can compute the reward. So I'm showing this to people to show that essentially you have something like 70 years of research to model things that led to that experiment. That experiment fascinated people, so they wrote another probably 1,000 papers on string stability and all these good things, until one article, Dan Works, in 2017, fixed it with an explicit algorithm using these models. Okay, and then one article managed to redo the same without any models. So essentially ignoring 70 years of history and managing to redo it from scratch using what you learn in this class. And for us, that was pivotal, because then we were convinced that if we can do this, it was not that easy. It seems easy when I say it, but it was not that easy at the time. Then it should work for much more complicated things. And so now the job was, now that we've done that, let's try to do Lego blocks and increasingly do things which are harder and harder. So first, we try to apply the same thing to lane changing. So if you try to stabilize the double ring, and you can sense backwards, okay, Tesla has backwards cameras, essentially what you should do is you should behave like a jerk, switch lanes back and forth and back and forth and back and forth to prevent the folks in the back from passing you at the right speed, and then you can stabilize the ring. This had been studied to death in transportation engineering, and the fact that you have a Boolean variable that encodes the lane creates a combinatorial optimization and it problem, which is not necessarily NP hard, but is so painful that nobody had really figured out to control lane changes. So here, okay, it just does it. And so you could agree, maybe this is a bit of an emergent behavior, because that's what you learn to do in the police academy. But it's amazing that it actually learned to do it, right? We didn't teach it to switch or whatever, it just learned to do it. So then the next question is, could you do more complex things? So then we looked at this other Lego block where you have an 8-figure and you implement general traffic rules. So if you implement general traffic rules, then the most possible inefficient things happen, which is everybody stops like a stop sign, and essentially that maximizes your fuel consumption because everybody has to reaccelerate, and that probably also minimizes your throughput. So it's the most inefficient thing you can do. Now you train the same algorithm as before on this, and what happens is this. So now I'm going to invent a good story as an emergent behavior. I'm going to tell you, well, the policy figured out the right speed at which to drive so that the length of the snake is exactly the length of the 8-figure. Because it turns out that the model is a car-following model, and the model adjusts its speed. If you drive very slowly, it's going to be more adventurous and goes closer to the car. And if you drive really fast, then it drives further away because it mimics human safety. So here I just invented a story to post facto rationalize what the algorithm essentially rediscovered through the learning part. You could also argue that the algorithm rediscovered platooning. So these are the trajectories at the intersection. When they go this way, it's eastbound, and when they go that way, it's northbound. And essentially, you could argue, well, it rediscovered how to create a train, which is another way to rationalize that. In this example here, where essentially I'm trying to maximize the throughput at the junction above, if I just have people drive like they usually do, then it's the same, right, left, right, left, right, left. So you'd use the typical stop sign policy, which is very inefficient. If I use the same algorithm, where now I also have the extra complexity of routing, So the red car can decide which route to take and can decide when to stop. And it can send some blue vehicles, which are random here. I really cannot invent a convincing story. Okay, it's doing something, it's clearly better. You look at the reward function, it's clearly better. But now it's very hard to tell you what it's doing. So that's exactly why we were convinced at that time when we got to that example that we were on the right path, because if you want to devise an explicit controller for this, I would not even know. I mean, I'm sure there's creative ways to do that, but that's really not a good approach to the problem. So then we went to try this even further by trying to see if we could do some transfer learning, where you actually learn on the ring, and then you deploy in a setting that you have never seen before. So for that, the learning is now the learning set has to be a bit wider. So in previous things, I've shown one ring with one red vehicle and some blue vehicles. Here, I'm not going to go through the details of the process that was used, but we teach the policy to essentially operate on that ring with several vehicles together. And that's important because you're going to see where I deploy it. And then we try that on this junction here. So I'm going to skip that curve. I'm sure you have computed such curves in this class. And so here's the setting in which you deploy the transfer learning. So every once in a while, you inject one of these vehicles on that junction. And what that does is it creates a backwards propagating shock wave, which is the source of this instability. That's another way to generate these waves. So it's like you jump in the pool and that creates waves. Well, you inject a car and that generates waves. And so the idea is, okay, if every once in a while there's a red car that comes along and has some form of information, could what they have learned on the ring be deployed on that junction? And of course, you can see now these waves are propagating. They're pretty bad. But the point is that probably if there's enough red cars, there should be enough of them to make things better, which is what we'd like to do. So you can see, by the way, if you've never seen these waves, I mean, even getting a model to recreate these waves is not that easy because it doesn't come as a feature of the software, so we had to work hard at the models for that. So now, here's what happens when you deploy it. So notice on the road, every once in a while, there's a red car and blue cars in front and back, and you can assume that any red car knows any other red car information and any other blue car information, because the whole system shares it. And what you see now is that you have essentially transformed a car into a red traffic light. That car stopped to reconnect with the thing exactly at the time it should, so that the waves is suppressed, but it doesn't, again, like it's happening again, but it doesn't propagate. And that's something it learned on the ring. So that I can actually rationalize, again, because it's a single lane and it's not very complex, and I'll explain in a minute. And that will be an opportunity for you to learn a tool that is commonly used in transportation engineering, which is called a time-space diagram. And that time-space diagram will be the tool we used for the big experiment. So here, what happened is the vehicle, again, learned to become a traffic light and to reconnect with the string in due time. So if you look at this in terms of trajectories, if you've taken any transportation class, I've never taken any, but if you have taken any transportation class, you've seen this, and if not, it's pretty simple. It's essentially a bunch of trajectories. The bottom is the time, the top is the position, and the color encodes the speed to give you some visual intuition of what's happening. So on the left, you can see the genesis of these shock waves. These shock waves, they are originating from what you saw in the movie, and you can see they propagate backwards, and they create this stop-and-go phenomena that you see here. Notice, I don't know if there's a pointer here, and I don't know what's happening here either. Does anybody have a laser pointer? Or okay, if not, that's fine. Okay, then I'll just jump or show with my hands. Okay, notice the first gap on the top where the big red wave emanates. That's because there's a trajectory that starts there. That's a guy that just entered the freeway and created that thing backwards. So that you can see one perturbation, boom, propagates backwards. Notice the transfer learning that happened on the ring has taught this guy to become a traffic light. That's what I was saying. And so essentially you can see it's just preventively slows down and then reaccelerates to re-engage with the stream of traffic right when it's not disruptive anymore to the trajectory over there. And so that's essentially what we tried to do 2 weeks ago when we did that big experiment with 100 vehicles. And that's what gave us confidence that hopefully it could be done. And Now here, there's a lot of issues about the information pattern because you need to know what's happening ahead of time. And in some ways, you need to know and cheat and know who is going to come in the next 2 or 3 minutes. And that's something that is complicated and we'll have to deal with in real life. Because here, not only you have full knowledge, but you also have advanced knowledge of what's going to happen, which is complicated on a real freeway. But we'll leave these technical questions for the end. So when we did this, then is when we started working on that problem really seriously. So the two students, Eugene is now a professor at NYU, and Abudi is graduating in a few weeks, did that interesting penetration studies to try to answer the question. Is like, okay, so if you can do it, how many cars do you need for it to work? How many, so if you pass 2,000 vehicles an hour on that lane, how many of them need some degree of automation for it to shave the traffic? And at the time, with this one lane example they did, essentially they thought that 10% would do it. So every 10th car should be one. Okay, of course we can never afford that. That's way too many cars. But that's if you want to fully remove the waves, which is also not what, I mean, this is maybe a too big and too ambitious goal. And so a lot of the diagrams you'll see will be of that nature, so always time and position, and ideally it should all be the same color, whatever the color. When it's all green, that means everybody is 65. When it's all orange, everybody is 35. But the point is, this is the average speed. The most efficient way to drive at that average speed is essentially to have no acceleration, no braking. And so that became our goal. And of course, if you take this class, you know that, okay, it's not, there's a lot of things that are complicated. Like, for example, if you try to minimize energy, there is a solution to that problem that deep reinforcement learning finds really fast. It stops every car. Because the best way to get to zero energy is to essentially stop your car. And the algorithm doesn't know that until you find these ridiculously stupid solutions. And so there's a lot of tweaking in the reward function that has to be done to achieve all these objectives simultaneously. You want to conserve the flow downstream and upstream because that's your demand. You want to minimize your energy, so you want some weight on the energy function. And then you want to push cars at a sufficiently high speed for other reasons. So a lot of the work is of empirical nature here because it's essentially trying to, it's almost like a form of multi-objective optimization in which one doesn't completely supersede the other. You just have to sufficiently satisfy all of them together. So before we went into the hardware world, the students continued to work on interesting things. So this one was an interesting concept that Eugene tried a few years ago, where instead of doing the usual metering of like the Bay Bridge at a given location, where you block cars and release them in sequence, maybe you could do adaptive metering, where you have essentially flow smoothers that enable the thing to never choke. That worked really well in software. And then, of course, the implementation on something like this is much more challenging. I'm sure you've all driven that bridge. We never pursued that, so if any of you is interested, maybe there's something to be done here. But could you do this on an actual model of Bay Bridge? And that's, okay, this is, I think, very hard. But that's something that probably in the next 30 or 40 years, this probably will become a reality. Like maybe they'll unmount the metering lights of the bridge, which, by the way, were built in the 70s and instrumented in the 80s by UC Berkeley professors. The algorithms are still the same, they're still running. So maybe in 20 or 30 years, they'll unmount the lights and then they'll be done by vehicles. But this is very hard. So we try to push that software approach as far as we could. And at some point, we realized, well, maybe there's not much more we can do, and now it's time to really go to the hardware world and try to make it work in reality. So we did a bunch of settings. Some worked better than others. Some people are still working on it. And at some point, the digital world has also its limits, so it becomes interesting to see if that can be pushed to the field. And at that time, in 2018, we released that open framework. At the time, we believed we could become the Mujoko of traffic. And that's another open thing. If you're interested to create a Mujoko for traffic, it doesn't exist. And the framework we have developed could be used for it. That's another thing which would be an interesting thing which we didn't have time to do because we wanted to get closer to doing it in the real world. But I do believe that it'd be really cool to have, you know, Mujoko enables so much benchmarking in the robotics world that I think it would be really nice. In some ways, the traffic world is equally messy to the robotics world pre-Mujoko, where everybody's running a different algorithm on a different model of the same thing on a different platform, and it's completely impossible to compare. Well, that is still a reality of traffic engineering. So there is certainly room for something here. So we had a first embryonic version of this where we essentially built a leaderboard that enabled us to benchmark algorithms that were developed on the same settings, and we mostly used it internally for our own benchmarking, because leading to the test we did 2 weeks ago, we had dozens and dozens of algorithms, and we wanted a selection process there. So we built it as our own dog footing, if you will, used it internally. That could be released one day, and that's something we're still very interested to do. So as we were continuing to dabble towards that experiment, Fengyu Wu, who is still a student here, had another idea, which is another thing which will happen probably over the next 10 years. And again, if you're interested, maybe that's another thing to do, which is to commit more traffic crimes. Okay, let me explain what that statement means. In the view of some people, not doing an analytical model of traffic, so reinforcement learning on simulation is a crime because it violates physics of the world. So we're going to push that criminology analogy even further. If you think about reinforcement learning and the way it operates, the environment produces a simulation for us. That's essentially the trajectory of every vehicle and all the parameters of the vehicle. That produces a reward that you can compute from the trajectories. So if you have full access to the trajectories or partial access to some of the trajectories, you can compute your reward, and that's what you use in your reinforcement learning algorithm to essentially improve your controller or your policy. So whether you have full state access or partial state access, let's say you can reconstruct it, ultimately that's what you use to train. So then Fengyu had an idea. He figured, well, what if we used pixel learning instead? And by that, what I mean is, what if instead of actually cheating and looking inside the black box at all the trajectories and extracting what's good for our reward, what if instead we looked at the picture of it? And there's a motivation, right? Because when you do pixel learning, the complexity, the complexity of a picture is driven by its size, as opposed to the state, which explodes with the number of vehicles. So that's why I'm saying it's kind of another crime, because now not only you've discarded the physical model of traffic, but you also discarded the state space. You're just looking at its rendering. And it turns out that on these simple examples, if you modify the reward function that you use in the machine learning algorithm, you can actually, in some cases, almost equally match the performance of your reinforcement learning algorithm, at least on the ring size and the 8-figure size. And the interesting part of it is that this also enables the decentralization of the algorithm, if that was of interest. So for example, say you have a city, this is the mini city of University of Delaware, and you were flying a helicopter and just looking at a picture, you could use this in your reinforcement learning algorithm, or you could assume, I'm just going to be myopic and see what's around my car and use that. So it's interesting because this is, and again, there's still a future in this and another project for people interested. This can be pushed further. This is just the beginning, but you could learn to control traffic from just watching traffic. And the reason why that's technologically interesting, which you will see in the data we gathered two weeks ago, is that even from a vehicle's perspective, the fact that you can do segmentation and do all the essentially onboard parameter estimation for the vehicle near you is a reality which every car will have probably within the next 10 years coming out of the factory, which means technically if you can watch some part of it, you could now start to learn and control from it without even having access to parameters of the vehicle, whether you watch from the air, video cameras, or whether you watch from the car. So that was another interesting thing we branched here. It's not done. There's a lot of work to be done here, and this also has a lot of interesting technological future. But at some point, we decided to focus to do the mega vendor test. So we kind of dropped that and decided to chase our real ghosts, which are the phantom jams that happen on the freeway every day in almost every country of the world. So 2 examples here. So you can see there's no reason for this, other than the human is very inefficient at driving, period. And this is a reality of every day. So we decided this will be our first objective. And now everything we're doing, all the eggs in the same basket, let's just to focus on that problem. So our mission statement became flow smoothing. And it turns out we had a model of the I-10 fully calibrated from the California Department of Transportation. So we thought, OK, we'll do it in California. That's cool. And essentially, our job now for 4 lanes of this freeway are to transform this phantom jams into this, which is like you take my 7-year-old, she put her both hands in the paint, tries to smear the paint to the same level of color, and that's the most efficient way to drive that freeway. So that became our mission statement. So every time you see these waves, they're just things you want to eliminate. So the model in question is the model I showed you before. It turns out it had taken 3 years to humans to calibrate that model. It has crazy amounts of data, and it's able to essentially model a whole freeway system and connectors for 24 hours at scale with real demand, real people. And so we figured if we can train our algorithms on this, then we should be able to deploy it on the field. And at the time, we thought we're going to do it here in California, but something happened, and then we went to Tennessee, and I'll explain what in a minute. So Aboudi Kreidier, the student I was mentioning before, used that model with Eugene Vinitsky and produced another policy, same deep reinforcement learning approach. And so essentially, it's kind of hard to see here because it's accelerated, but it's operating on that freeway. And so what you see the big shock wave here. It's coming, and it's going to enter this. And right now, there's no control. So that's why there's no blue vehicles. It's just human people driving the red vehicles. And at some point, you'll see the vehicles turn blue. And when that happens, that means that essentially the controller is on, and it's going to try to smooth these waves that they're a bit hard to follow because their periodicity is slow. But you can kind of see them maybe in the little magnified vision here. So in about 10 seconds, the cars are going to turn blue, and when that happens, that means essentially now it's flow smoothing. And the thing to watch when it happens is essentially these oscillations, which you kind of see happen visually, now they turn blue, should be removed in the next couple of seconds. And I mean, okay, you can look at the numbers, or you can look at the movie, and here we were pretty happy. It did work quite well. And so at that point, so this happened maybe 3-4 years ago, we knew that, okay, it was worth trying to go, oh yeah.
What is the intuitive principle behind the smoothing? So because somehow you have like this artificially controlled car, which maybe slows down traffic to some extent, but how does this prevent all of the human controlled cars to still act noisy at a new speed or in a new
Okay, so for people watching online, I'm just going to repeat the question. Yeah, so the question is, what is the intuitive thing happening here, and what's preventing this from happening despite the smoothing, because most of the cars are driven by humans? Okay, so this is a very good question, and when we did it with real people in Nashville, you'll see it happening. So the intuition is very simple. If you're on the freeway and you're stuck in this, your natural reaction, if you're, I don't want to say a normal person, but like a statistically whatever person, is to catch up with the person in the front and fill the gap, period. Like most of the people do that. I do that, many people do that. That is the amplification mechanism. Because what happens is the phenomenon I explained at the beginning, you're going to catch up with the person, slow down abruptly, and that phenomenon is going to be increased and increased. So if you want to smooth, the intuitive or the non-intuitive thing to do, which actually works, is you see the gap forming in front of you. You don't try to fill it. You don't go too far either because that's extreme, but somehow you have to find the right distance that would work for the wavelength frequency at which you're experiencing this instability. That's the intuition, the physical reasoning behind it. Again, I'm giving a post-facto rationalization. I'm not giving you a mathematical proof of it. So the automation does exactly the opposite as what the human would do. And statistically, on the freeway, 90% of the people will just fill the gap because they're nervous, they want to get home. That's just human nature. So it learns to do the opposite of what you would normally do at the proper frequency and with the proper magnitude. So then, okay, the time had come to put this in hardware platforms. So you got to start small. We call them the babies. They were built by Fengyu. And so we managed to recreate these instabilities on small rings, and we managed to create algorithms to smooth them. So at least, and this had been an interesting case of transfer learning where we learned in software and deployed the version directly to the hardware platform. So it's like a kind of a good analogy of what would happen with the real vehicles. You need to be able to simulate in software and then deploy in hardware. Then we tried a few more complicated things. So this one was done at the University of Delaware with Andreas Malikopoulos. This is the work of Kathy Zhang and Eugene Vinitsky. So here was a sequencing problem, again, a different hardware platform. And so I guess the thing to watch is this is the same traffic scenario on the left and on the right. I'm going to replay it, sorry. There's blue cars, they are the smoothers, or they're the controllers, and then there's the other cars. Here, the objective function is to flush the ring the earliest time possible. So the blue cars are not only solving a sequencing problem, but also a speed assignment problem, so that the last car leaving the junction leaves the junction as soon as it can. The baseline is on the left, and the controlled scenario is on the right. And we were doing this both for the fun of it, but also for the sake of understanding how we can migrate and do transfer learning. And so you can look at the Hummer, or the whatever Humvee, or whatever the last vehicle. That would be the right, the last to leave the junction on the right. And you can see the other ones who are also looking at the traffic light, like they have to stop at the junction, leaving the junction and the ring later. Okay, so again, so this was our second hardware platform. So at that point, we felt that we can do more hardware platform, but it's almost equal amount of work than doing it for real. So then we decided, okay, now we're going to move to real cars. And so I go back to this thing where in 2016 or 2017, I forget, they had done this one car experiment I showed earlier, which stabilized the ring. In 2018, they had done an interesting other experiment, I was not part of it, where they had gotten 8 different cars or 6 different cars straight out of the factory with ACC on, put them next to each other, different cars, different models, and shown that even without human in charge, if you just put your ACC working together, then this also happens. So in other words, bad automation can be equally bad as humans. And this is stuff that you buy straight out of the factory. So that also convinced them of the value of what we would be doing for a different reason. It's like collaborative automation is needed. And so that convinced us to do our first test last summer with 10 vehicles. This was really the scariest part because it was a quantum leap for us. Even though the one we did 2 weeks ago was the most intense because running a 100-car experiment was really hard. So we moved, and now we decided to move to Tennessee for a reason I'll show later, is that at the time we were starting, Dan Work, the former student here who is now faculty at Vanderbilt, was also building together with the Tennessee Department of Transportation this crazy instrumentation of the I-24 in Nashville, where they deployed one video camera pack every 500 meters. These are super high resolution video cameras. I'll show you what they can generate. It's crazy. So this is the highest density of instrumentation of the freeway in the world. Like, I don't think anything like this exists anywhere else. So we figured the opportunity is too good to be true, because this is our only opportunity to do it, but also see everything happening on that freeway on that day or on that week, which is very important because remember, we only have at most 1% of the vehicles. The rest, they're not our vehicles. They're regular people driving on that freeway. So it'd be nice to have a recording of what they did. And so we figured, okay, we're just going to not do the 210 in California. We're going to do the I-24 in Nashville for that. So the reason why we did it 2 weeks ago is because 2 weeks ago was the grand opening when they turned it on. So we actually were the first experiment to run on that platform when they opened. So, so first we were a bit scared. So we did it at small scale. I'll just show you what it looked like. This was last summer in the middle of COVID, which was a bit challenging. So we essentially built a small field headquarters there. With help of the police, we positioned the cars in a funeral procession into the second lane or the third lane of the freeway, essentially running a form of caravan and trying to just do one lane at a time. So there was the first time, it was scary. So every driver in the vehicles were ours. We had regular vehicles that were just sensing, and then we had control vehicles that were smoothing, and then we had people kind of going on and off, changing lanes because they had no idea we were doing this because we didn't tell them, and also we didn't want our vehicles to look different. This was on the I-24, and this was long before they opened that test bed. And so it was pretty scary, but it worked. So we had also a team looking at what was happening on some cameras we had deployed. And essentially, this is what we were running at the time. So you can see we had 4 control vehicles in that experiment. I don't know why it's doing this, I'm sorry. We had a few blue vehicles, quote, which were the vehicles that we were able to see and monitor. And then a bunch of people that were coming in and coming out and we couldn't control. We did a bunch of scenarios. And this is the one, we made it, we had 7 days of testing, and we only managed to succeed at 1, but that was enough to get us to continue. And this graph was really what kept us running for 1 year. Because so this is what you can see. There's two waves. So this is real data now. This is not simulation. This is real. So this is probably 7 a.m. traffic-ish in the morning. And you can see the cars going through two waves. And then we computed for the control vehicles the savings in energy. That's the red bar here on different tests. And so first we figured out, okay, for our control vehicles, we can measure we're saving roughly 16% of fuel or energy. And then, of course, we didn't know anything about the people behind, which we couldn't measure at the time, so we just plugged that into a model and also noticed that that question that you just asked earlier, you know, the fact that this vehicle was saving so much by slowing down in anticipation forced the people behind to do the same. And that's how they save energy. So this graph was really cool for us because when we showed that to the US Department of Energy, we could legitimately say, look, it's not just good for you if you do it, but it's good for people behind you. And that's how we think we will be able to shave these waves. So this is the graph that kept us running, and we only succeeded once. So it's like, okay, we got one shot and it worked. And so, and it was hard because you can't really see on these graphs here, but these curves, they have jumps. Now these curves, they show the headway, the evolution of the headway, a bit, so which is the distance between you and the vehicle in the front. And when there's a jump, that means someone leaves the lane or someone joins the lane. So you can see there's a lot of messiness in the data that I don't have time to explain here. So this was our first thing. So now that led us to what we did in the last couple of weeks in Nashville. So the first thing that was important to realize is so there's an inherent need to cheat if you want to succeed. And the reason why you need to cheat is because you cannot push people faster than the capacity at the end of the freeway, and you have to deal with the people coming in at the entrance of the freeway. So in other words, if you know the speed at the end of where you're smoothing traffic, that's a huge piece of information. Because if you set your controllers at that speed, it's a nice way to smooth traffic. You know you can only flush, say, 1,000 vehicles per lane per hour because it's semi-congested. So if you know the speed, you can essentially inject that speed into your policy, and now you know the average speed at which you can drive. So if you were using like the military approach where you force people in lines to drive at that speed, essentially you could achieve optimality. So the interesting part with the machine learning here is that we also thought that without cheating, maybe there's a way for a policy to learn through a lot of different flow conditions how to infer that information even if you don't have it. And it turns out you can do it to a certain extent. And we thought we would be running it, but actually the story is a little bit more complicated. So the intuition here is very simple. And the intuition is given by that picture. Like, you just can't push it. If it's in front of you and it's deciding to go 5 miles an hour, well, you could drive over it, but that aside, this animal is driving the flow. And that's, so the animal is driving the flow means that the controller I showed you for the ring has the speed of the animal encoded in it. That explicit controller I showed you has very simple equations. This is what they run in 2017. And essentially, what it does is the following. Top line, if you're too close, don't accelerate. Like, okay, just you need to stop. If you're a little bit closer, do whatever is in equation 2 and 3. And if you're really far away, drive at that target speed. The target speed is the speed of the animal. That's simple, right? So this is something that they devised in 2017. That stuff works actually quite well. You can improve it. You can do a lot of fun things with it. But the point is, this is called the follower-stopper algorithm. And to make it work, you need to cheat. You need to know the speed of the animal, capital U. And if you know capital U, you're good. So then the question we asked ourselves, well, could we use a lot of different simulations to learn U from traffic? And the guy who had this idea was Abu Dib, and then Nathan Lichtle came in and tried to do the same. And so now what they started doing is, well, let's try this at 5 meters a second, 6 meters a second, 7 meters a second, and let's train a policy to learn that. And I mean, I guess the underlying religious belief or philosophical belief is that somehow the fact that there's this capacity limit at the very downstream part of the network propagates itself in some way if you know the simulation. So based on what you sense, hopefully you can pick some of it in your learning, and it will learn how to deal with it. So this was an interesting form of, I guess it's at the same time imitation learning, and it's also learning a parameter. But the way it worked, sorry, I have kids. I want to make sure that. Sorry. So the way it worked is essentially we trained it on a lot of different flow conditions with the hope that it would learn how to cheat that parameter. And it did work in some ways. And it's not exactly what we implemented. And so now I'm going to tell you what we implemented for real, or what we thought we would be implementing for real, because we don't really know what we did implement for reasons I can also explain. Okay, so this is the architecture of what we built. So there's a few important boxes here. The important box is INRIX, which is just a particular data source we use, which gives us forecast of traffic and also knowledge of traffic everywhere. And INRIX goes into Speed Planner. Speed Planner, we have Je sitting here. She's one of the students who worked on that. Is essentially a form of optimal controller that achieves a high-level goal of coordination based on real traffic data fed to the system over the cloud from other sources. And then that sends this into, we have different platforms and different vehicles. We had 102 vehicles of different brands. And then you have a local controller in this blue box in the bottom, different vehicles, that does what I was just showing now, except it did it in machine learning. And so this is, we call this the mega controller because we were pushing different algorithms to different vehicles at the same time and running this on heterogeneous platforms. So we called it mega controller because it had all these features. And so let me first show a little bit of that problem. I will show what we wanted to run, even though what we did run, I don't have for you today, but I'll show it to you. I'll show the data, but not the results. So INRIX looks like this. This is what you can buy. You can buy that data. You will see these waves, but it's very coarse. And that's what you use to forecast. And you can detect bottlenecks, that these are like stopped vehicles, or you can detect shock waves. And so the Speed Planner essentially took that information to figure out the way to do it. What that means in mathematical terms is, I'll use these are my only 3 slides where I have some equations. But in optimal control, one way to think about this is you have these red controller, which are trajectories you can control. You have these blue controllers that react to it. This is the work of Arwa Alankari. And then essentially, you have some form of coupling of the two. And what you're trying to do mathematically is you're trying to find existence and, if possible, a constructive way to build an optimal controller, which is essentially a signal to the red vehicles that optimizes a function within a certain class. If you can prove the existence mathematically, you know that at least it's there. And if you can construct it, it's even better. And so you have some form of optimal cost function. If you have taken any optimal control class or E227, probably you've seen this. And essentially, the main result is you can prove the existence and uniqueness. In some cases, it's not unique, of the solution. And then if you're able to, you can also compute it numerically. So this is essentially what this thing is doing at the high level. We tried many, many different ways. The one we did with Joe's algorithm in Nashville, a different version of that. But that's essentially philosophically what it's trying to do. So in practice, what it does is it tries to figure out how to solve that shockwave problem. So you have these shockwaves. And this is an example of a solution to that problem, which is not a good one, because it creates too much gap in between the vehicles. So we tried a bunch of them, and sometimes it's interesting. Like this one is clearly better. So it creates less gaps. And so a lot of the work that preceded the work in Nashville was essentially trying to construct that Speed Planner work. And then the machine learning happens at the level of the vehicle, mostly for local control. Now, here, when we started, we assumed we could measure the headway. We assumed we could measure the relative speed, the relative acceleration, because the ACC already has that. And it's not until we got the vehicles that we realized that's not necessarily true. So it's crazy, right? But we had a vehicle from, I think, 2018. And in that vehicle, we could access everything. Like, we could know how far ahead the other vehicle is and blah, blah, blah. Well, it turns out the next year's vehicle, same brand, we couldn't access it anymore. The autopilot can access it, but we can't. So we had to figure ways around it, and I'm not going to have time for that story today. But the point is, like, what we thought we had, we didn't. So we had to also work on our algorithms to factor in for that. So what we thought we would be running is that algorithm that I told you that was learning from by cheating and learning by doing more and more simulations so you could infer the parameter. So this curve is something we're really happy about. Every time you have a green curve, it's a specific algorithm, so a follower stopper that is cheating for a specific value. So for example, if you look at 3, that's the downstream limit 3, you can see one of them set up for 3 does the best job for that. But anywhere else, it fails because it's not set up at the proper speed. And so what was really cool is that we managed to train the blue algorithm, and it's not perfect. Look, at low speed, it didn't work quite well. But what was amazing is that it had learned across different outflow speed to almost outperform, or at least perform as well, as the algorithm that are cheating, but without that information. And so this is what we thought we would be running. At the end, we had to run something a bit simpler because of that sensing problem. And so that's essentially how we implemented this test in Nashville, which I'm going to show you now. And I confess I finished my slides a few minutes ago because I think you're the first one to see it, because we've never given that talk before, because we've not even, I don't even have results. At most, I'll show you data, but I don't have results. OK, so this is what we implemented. So first, the site. This is the I-24. This is when they were building these poles. I don't have good pictures of the cameras, but the cameras are quite amazing. This is a movie of when they built the 3 first ones with my student Dan Work. So I mean, this gives you a magnitude of what it took. I mean, this is a $15 million test bed that they built, not just for us, but we were the first user of it. So you'll see them erecting these gigantic poles, and you probably will not see them mounting the cameras on them because that comes later. Okay, so that gives you a sense of what we have. We have this every 500 meters, and on the top of it, there's a 6-pack video camera system that has amazing accuracy. It's kind of crazy. You'll see the data we can generate from it. So you can think of this as this is our eyes in the sky, and this is what we use to measure everything happening on that freeway on that day when we operate, not just our vehicles but the other vehicles. Okay, so that's the test bed. This video is from a different source, but that gives you a sense of what we can get. And also all the good machine vision stuff that quote comes for free, we can also, it's not easy, but we can essentially identify the vehicle class. And in some cases, we can even identify the vehicle type. But the class is easy. The type is a bit harder, and we don't really need the type. But the point is that whole software stack that they built with that testbed at Vanderbilt enables us to essentially identify vehicle penetration. So we know we have 15% of trucks, 10% of pickups, 20% of sedans, etc. So this is something we assume we can do. So then this is when the story begins. So I like to show this because this is really the way it feels. So I don't know if any of this is part of the movies you watch, but there was really a feeling of, there's 50 people flying in together who, for some of them, I've never met, and are somehow able to function for a month at doing something crazy and then go back home. And so this was the team. We flew there at various times, and essentially we built a 200-people organization, which we just dismantled a few days ago with our own payroll, and that's kind of what it looked like. And now I'm going to tell the story of how we did it. So it's kind of like in the movies in that, there's 50 people managing this, and then there's going to be 150 people driving because we need real drivers. It's not fully automated. So we built our headquarters in an old a corporation factory that we found. We started assembling the hardware. So you can imagine assembling hardware that we're going to plug in vehicles for 100 vehicles takes a lot of time. The Vanderbilt team had started working on it, and so essentially we assembled our own factory, quote, to do that. Uploading software, pushing software to vehicles multiple times a day required our own communication infrastructure, so we also built our own internet, quote, so that we could essentially upload and download really fast to all the vehicles and push different versions. I show this because it's interesting, right? In 2018, at the IEEE ITSC conference, I spoke with a major manufacturer of luxury vehicles. They could not do this on their vehicles in 2018. Some companies that start with a T can do that routinely nowadays, but it's not a given that a company can push hardware like this, software as this on demand, like their platform doesn't necessarily support it. And so then, this is actually from unmounting, even though I'm showing it in mounting. comes the scary part, at least it's scary for me because I've never done this, is a grad student who is an unbelievable genius at hardware, actually 2 of them, explained to me and to the whole team how to take a screwdriver and start unscrewing this part of the vehicle, do it 100 times, so that will take a couple hours. So there's 50 people doing this in parallel. And then he will come and unplug this wire, and then he's going to give me the screwdriver again, and I'm going to rescrew. And then we're all going to rescrew. And then we're going to, there's like dozens and dozens of such operations. So we took the 100 cars out of the factory. They were brand new. And under the supervision of these 2 students and their advisor, John Sprinkle, who is a former postdoc of Shankar Sastry here, essentially actually I didn't even know what I was doing. I was just told, take the screwdriver, do this, do that. Take the cable, do this, do that, and that's it. And so here's an example of Gracie Gum, one of the students who is showing us how to take off the cable from the battery so we can hook something up to the battery to power our own electronics on board that vehicle. Here's another example of a side panel I take off so we can access another cable that goes to the autopilot. And then somewhere in the middle, there's the secret cable, which I don't really know which one it is, which is how you access ROS, which is essentially the operating software for the automatic cruise control, which is what we're overriding to put our own policies on it. Okay, so this part, to me, this was probably the most exciting part because now I know how to take a car apart, and that's fun. And then the infrastructure we had built, so that's kind of what the quote dirty electronics looks like in the back. It's a simple Raspberry Pi plus some other instrumentation we do, enables us to push next version of the controller on a daily basis, depending on what we need to push. Even though it's actually quite painful because if you want to see, I mean, if you just think about that process, right? So you have 100 cars, you're pushing software, so first you have to turn on all the cars so that the electronics wanders. So that process already takes you 20 minutes because there's 100 cars to turn on. And then, so it's freezing in the night when you do that. And then you essentially have to push, check that it works. There's a bunch of tests, and then it shows green. And when everything is green on that screen, that means you know that all the cars have uploaded and updated their software properly. So we did that routinely until we knew how to do it. The first night, Professor Maria Laura de la Monaque, who's a UC Berkeley prof who also was there, she walked 18 kilometers in that parking lot just to check things one by one. So that gives you a sense of, it's kind of, weren't really ready for it, but anyway, it did work out. So then the next problem was how are we going to get 150 drivers so we can have enough drivers to drive these cars. So it was kind of another interesting thing in the in the project where suddenly overnight, like a few of us went to the Vanderbilt campus and started to try to recruit students. And it is actually not that easy because you have to wake up at 4 to show up at the bus at 4:30, so you could be on site at 5:30 and start the whole day of work, and that conflicts with midterms and exams. So when we run out of students who were willing to do it, well, first we doubled the pay to $200 a day, but then we became really desperate, so we went to the Uber terminal, to the bus terminal, to the cafeterias, and started to give the flyers away. I'm very proud. I recruited the girlfriend of my Uber driver. So essentially, I gave the flyer to my Uber driver, and then the next day, she showed up and said, "Hey, I'm the girlfriend of this person. Thank you for recruiting me." And bus drivers and whatnot. So this is what it takes. So we recruited 700 people. Then we had to create a background check for them. So only 210 were kind of cleared because either accidents or didn't file the paperwork properly. We invented our own payroll, and essentially we ended up with something like 140 that would come every day, and for maybe something like 100 would be on the road at a given time. At some point, we managed to have 100 cars on the road at the same time, and that was really cool. So then we had to do driver training. So all the people wearing blue vests, that's us. All the people wearing orange or yellow vests, these are the orange drivers and the yellow drivers. You'll see in a minute what that means. And so then we had to teach them, okay, what to do, right? These people, some of them, they're retired. Some of them, they work in a shop. Some of them, they're students. Some of them, they're bus drivers. But they have no idea what we're doing. So we teach them. It's relatively simple. And then we have to manage them because it's 4 in the morning or 4:30 in the morning, and you have 150 people there waiting to work, and you have to have food for them and all kind of logistics. So we had to create some kind of a pedestrian management thing. And then we taught them what to do. So this is what it looks like if you're in the car now. If you're in the car, if you're a driver, you're going to drive for 4 hours a day for us. You're going to be paid $200 per day. And all you have to do is very simple. You have to drive safely, not have an accident. Well, it's not easy, but okay, because that freeway is crazy. But you have to do that. You have to engage what you think is the autopilot. That's the blue onion here. You push the blue onion. it engaged the autopilot, so the ACC, and then you have to, so that turns it on, and then you have to engage it. That's the right movie. That means essentially now it's got to operate. So it's simple, just that's it. And then we tell them, but okay, just be aware, it's not running the thing from the factory, it's running our thing. So if it feels unsafe, if it feels uncomfortable, if it feels dangerous, turn it off, disengage as you would do, you brake or you disengage, and then you just drive normally. So this is the experience essentially from a driver's perspective. So once they knew that, then we feel they were safe to be put on the road, and it looks like my computer froze. So then we had two routes. So they would take their phones, they would have everything in paper, but they would click on the QR code, and then they would be taught what to do. So there was an orange route, there was a yellow route, and essentially they were driving back and forth, and we told them there's a cutoff time, come back at that time, or if there's anything you're unhappy with, then just come back and we'll rotate you. And then while we were doing this, we worked very closely with the police department, so they would help us in case of any difficulties. We also had a monitor that was built by Johnny Lee, who is our PM here at Berkeley. And essentially, we had the I-24 motion system to monitor everything, which I will show you in a minute. And we even had our 800, we even built our 800 numbers so the drivers could call. We had our own call center. And then they essentially, a few of them called, and we helped them when needed. So these are the cars we were running. We had 100 Nissan Rogues straight out of the factory, brand new. We had one Cadillac XT5, really nice car, and then we had 5 RAV4s, 2 of which on the site and only 1 on which ran. So total of 102 cars run on that day. And essentially, this is what we run the experiment with. So we had to getting 100 cars in and out of parking lot in order to sequence is actually not that easy. So we had our own parking management crew that was essentially managing this like an airport. And then as the drivers were going out, this was probably the most stressful part for 2 of our PIs, Dan Work and John Sprinkle. You know, you're going to put someone's life in the hands of your algorithm. It's very scary. And so every driver, before they drove off that parking lot, received one last final briefing from one of the 2 Vanderbilt PIs. And yeah, it's hard to describe what they told us, but it's like there is this feeling where, you know, it's like a test pilot. It's not as critical as a test pilot, but the thing is, this is the person you recruited yesterday at Safeway, so there is a bit of a responsibility there. And so they essentially put them on the road. Once they had received their final safety briefing, they were allowed to proceed. And so that's what it looks like. So essentially, it's managing this like the airlines. You want to have aircraft in the air almost all the time. So you try to rotate drivers in and out as fast as you can so that you maximize the time when the vehicles are on the road. And so this little clip here is a span of about 3 or 4 hours. And every once in a while you see different batches of cars. That's because we're running different algorithms, so they take different procedures. But essentially, that's what a day looked like. So the day started at 4 a.m. And by the way, if you could stand up like Avikam and Je and Adit and Anish, just there's a few students, just I'd like to acknowledge you because you were there. Yeah, if you were at, so yeah. I mean, we all showed up at 4 a.m. to be ready, and then did that in the morning, and then did the algorithms design again in the afternoon, and pushed the code in at night. So a lot of different people involved. So if you were on the road, that's what it would look like. So essentially, this is I-20. This is the real traffic we smoothed on, I think it was Wednesday, and then this is the vehicles proceeding to one of the tests. And so, I mean, okay, it's kind of boring to watch traffic. If you're running 100 version of your algorithm and there's real people, it's a little bit more adrenaline generating. But the point is, this is the kind of traffic that we smoothed. And even though now it looks pretty peaceful, I drove on that rightmost lane. I enter the freeway. Within 10 seconds, there is a guy who passes me on my right, the shoulder lane, at 50 miles an hour. Okay? I mean, seriously, the driving there is different than driving in California. I've seen people walking on that freeway. I've seen a lot of different crazy things happening on that freeway, so it looks pretty peacefully from that drone shot, but it's actually not that peaceful. So it did work quite well. The media was on site. We did a big press conference. This is Arwa. She's giving an interview. She's another PhD student here in the EECS department. And we got a lot of press coverage, and it was really great. And now I cannot show you any results, but I'll show you a lot of data. The only thing I can show you in terms of results is on Wednesday, we ran nearly 1 million trajectory segments. That's about 6 times around the Earth in terms of distance recorded in the data that I'm going to show you. We cannot make an assessment of how much energy we saved or wasted, and I'll explain to you why in a moment. That will take several months before we can do that. But okay, this is our first definition of success was to run the test, and now we probably have 1 year of data analysis to figure out what we did. And here's why, and this is really a pitch for engineering and data science. So clearly, this was, in our knowledge, the largest flow smoothing experiment in the history of traffic engineering. This was also an engineering achievement for us to have an architecture that can support pushing things on different platforms in real time. It's not that easy. And again, in 2018, a lot of car companies couldn't do that. And even to this day, I bet you that some car companies can do that. We created dozens and dozens of algorithms, and I've shown you a few here, but I think each of them is at least a PhD talk of a student or at least a seminar talk. And then the one thing we really did not realize is that even though the car has access to all the parameters around it, the blue cars, we don't. So once we had all these algorithms figure out what to do, then we had to figure out how to retrain them so that they would do it without seeing as much as we thought they would, and that was hard. And then the real question, and the reason why I cannot show you results other than the data, is because somewhere in the data it says, okay, at this time of the day, the person had the algorithm on, but then at that time they stopped because they were scared. And then at that time they re-engaged, and then they stopped. So it's going to take months. That data is there. It's not that we have to fish for it, but it's going to take months for us to make sense of that data, and that's also an interesting data science problem. So at the end, we have the largest trajectory data set in the world for now. The final energy estimates are going to come in weeks, if not months, and same with the detailed flow. So let me show you the data, which is really all I have, but it's fun. I mean, okay, everybody who has seen that data live, I think I had a big smile on their face. So first, the video data, I mean, it's hard to even comprehend unless you watch it live. But so this is, each of these little things is one of the little cameras deployed along these miles of freeways. And behind is a bunch of algorithms that can do vehicle re-ID. So you can essentially stick the trajectories together and access everything from speed to headway to many other parameters. And even acceleration apparently is something they can extract from that data, which is still mind-boggling to me because this is not work I've done. But that's amazing too, because that's usually hard to get from odometry, and this I know from other applications. So the data, if you look, that's what it looks like. Each of the dots, I forget at which frequency it's actually rendered, but it's video data. So video data is sampled at a very high frequency compared to other sampling frequencies. So, but there's too much data that we can't even represent it all. So each of the vehicles here is represented by something that you can visually infer as a trajectory. And the reason why they cross is because right now we're representing the 4 lanes on the same plot. We don't even have proceeded to the point where we can lane separate, it's trivial, but we have not even the tools for it yet, because this is the first time we're seeing this data. And then the white trajectory is one of our vehicles, one of the flow smoothers. And again, we have not even started analyzing what they're doing. And I'm not even sure on that day I'm showing you here whether we were just running an ACC to compare it as a benchmark or our stuff. So don't even try to infer what it's doing because we have not even started. And then you can see, so I'm going to zoom progressively to show you the data we generated. So that gives you a sense of the magnitude. And also, you know, if you're running 100 cars, I don't know how many we were running on that day, that was Wednesday, you know, you can see it's not that many. And so once we show whether we succeeded or not, which I still don't know at this day, then, I mean, that's what we're working with. And again, you know, if you're thinking to count the number of Teslas at Page Mill Road in Palo Alto, I bet you that the penetration of Teslas is already way, way, way higher than the white vehicles here, which means it's not science fiction. Like, this could be done in a not so distant future. So this is, now if I zoom even more, you can see these big waves, right? I mean, they're not a fiction that we create in models. They're actually the real thing. And actually, one surprise even from that test is there were way more waves than we thought there would be. Like, we went into this like a surfer goes to Santa Cruz and thinks, well, if I'm lucky today, I'll catch some good waves. I mean, they were just all the time, all over the place. Like this was a big surprise. And you can see throughout the entire morning. Of course, you have to wake up at 4 a.m. to be on the road at 6:30 a.m. to catch the waves, kind of maybe like in Santa Cruz, because this is during congestion into Nashville. But that gives you a sense of the potential of this. And so this is, I don't even know if we have a way to save all the data into one single picture. This is roughly the duration of 1 day of experiment. You can see in the morning there's not much, and then at some point it starts to be really bad, and at the end of the morning it stops. And this is I think when I saw this on Monday 2 weeks ago, I think nobody, including in our team, had seen this at that scale. This was the first time we saw this. I don't think anybody has seen data at that scale. The first time in history this was ever plotted was in 1960. It's a 10 by 10 matrix. Alex Cabardones has it. It's crazy. Okay, but I don't think before 2 weeks ago anybody had seen anything like this at that scale. And certainly when we started controlling with the y trajectories, it's also not something that has ever been done at that scale. And so you can see why. I mean, the only thing I can show you today is really the outcome data, because it's going to take month and month. But for us, when we turned that on, I think it was just a magical moment, and this is really a tribute to 2 of the students who are shown here who have done this. It gives you a sense of what we were watching there. So this is my last slide, and I mean, there's 50 people who just flew for that experiment. I cannot thank everybody, but I just want to say a big thank you to, first, if they ever watched that movie, that YouTube video, the PIs at Vanderbilt, Dan Work, and John Sprinkle, the PIs at Berkeley, Maria Laura de la Monaque, and Jonathan Lee, and then the PIs at Temple, Benny Siebold, and at Rutgers, Benedetto Piccoli. I think this was a crazy team to work together. All the students and all of you who came were amazing, and of course a lot of people in these organizations who funded this work, which was quite privilege and honor to be working with them. So I think that brings me to the end. I think we might have a few minutes for questions. And yeah, thank you for coming. Yes?
Thank you. It's very inspiring speech. So I have a question about when you mentioned transfer learning in reinforcement learning for transportation. You mentioned something like the flow project was designed to be the logical in transportation, right? What do you think it's important to build a simulation of transportation? You mentioned about car following, you mentioned about lane changing. What's the important points to build a reliable and high fidelity simulations that we can trust to run our reinforcement learning on that and deploy in the reality?
Yeah, this is a fantastic question. I'm going to repeat it for whoever watches the video later. What do you need, or what are the things you need to build inside a transportation model for it to be the right tool to learn in a deep reinforcement learning framework like here? Okay, so this is a fantastic question, because we sweated. You know this because Jay was there for part of that. It took us 2 or 3 years to figure out what we needed and why we needed it. So the first thing you need is you need a model that drives like a human. So you need what's called a car following model, or a follow leader model, that is representative of a human. And a Californian does not drive the same way a Nashville person drives. I can tell you that. So and then, okay, once you have this, you need to have a distribution of people. Bus drivers, truck drivers, human car drivers don't drive the same, so you need the penetration rate of the vehicles. Okay, so what that gets you is that gets you the first part of the talk. That gets you algorithms that can operate in the real world. And if your models are good enough, how do you define a good? It means like someone should not do something that a human would not do. So there's a distribution of accelerations. You cannot do 15G with a car, etc. So once you match these parameters, then you know you have something which is somewhat representative of a human. That's part 1. Part number 2 is you need now a model of demand. I-24 has a pattern. In the morning, congestion builds up at a certain time, dies at a certain time. That's demand data. So that's a completely different set of parameters you also need. So origin, destination, and dynamic traffic assignment. Okay, once you have that, you have I-24 with real-looking people, but you don't have the waves, because the models also need to encode the waves. Now the problem is that's harder, because the waves now you need to be able to model that instability. And once you have the 3, then maybe you have the ingredients to do to teach an algorithm to behave in that setting in a satisfactory manner. So you can see these are very different difficulty, and that's why your question is really deep. You need to not violate physical laws of people driving. You need demand data, and then you need instability data. Yeah.
Yeah, a related question. So using these more sophisticated simulation models that you guys have made, say we were simulating San Francisco traffic, for example, what are the limitations now of these simulations? And yeah, the reasons that you wanted to go into the real world.
So for the audience, the question is, what are the limitations of these models if you were to go in the real world, especially if you were doing something of the size of San Francisco or with San Francisco traffic? There's multiple limitations, and these models are still challenging for San Francisco. San Francisco has 750,000 people, intramuros, probably 2 million, 3, 4 million if you factor in all the Bay Area traffic. So at a given time, you'll have you have tens of thousands of vehicles with much more complex dynamics than we have here because of the traffic lights and because of all the other things of urban settings. So something like San Francisco, you can probably do a tenth of it. To do that, then you need a lot of additional features in addition to what I told you, because now you need a traffic light, you need a bunch of other things which you can imagine from traffic. So bottom line is, this does not work at the San Francisco scale yet, but my corollary answer is we don't need to, because some of the features we're dealing with here are inherently local, and so there's no need, if you want to optimize San Francisco, to optimize it all at once. And it depends on what you're trying to optimize, whether you're trying to optimize the overall mileage, the overall travel time, the smoothness. So in some ways, this is a good model this is a good family of model to use for what we did. But for San Francisco, you would want to use different versions of this, or different decentralized or parcelized versions of this. And also, I don't want to take credit for the models in that we did not invent the models. I mean, there were commercial platforms and there were open source platforms, but our contributions were to take these models and customize them for what we did, which is an important distinction. Yeah.
So this is like a kind of a very general research process question, right? So the experiment is clearly extremely labor intensive, right? So I wonder if this is like a very open-ended question, but something I think about a lot. I wonder if you could talk a little bit about how you see the trade-offs between the kind of fast iteration that can be done with the simulator versus the kind of things you can learn from doing, kind of the medium-scale experiments with the little toy cars versus the gigantic experiments. And I guess somewhere lurking behind that question is like, is it worth the effort?
Is it worth the effort? Yeah. So for the audience, the question is general philosophy between fast iteration, things that can work in the lab, in simulation, or with some amount of hardware, and something like this, which is crazy that, is very labor intensive, and was it worth it? Well, the truth is, it's not like the Artemis launch. We had a deadline, and the truth is, by the time we got 1 week from the deadline, we finally were ready, but we would have needed 1 more month to do the more algorithmic work, because it's only then that we understood the difficulty. So maybe for that reason, the results we might get might not be as good as we expect, or maybe they will be, we just don't know. But maybe it's a hard philosophical question, because everything worked beautifully until we put it on the road. So in many ways, my life was very happy in 2021, early 2022, because in software, it always works. And on the babies, like what we call them, it always works. And on the University of Delaware thing, it always works. And when we try to implement it, everything broke. Like, I think the worst and most shocking thing for us was the fact that it's not even 3 months before the actual test, when we get the 2023 car, we realize that the 2023, even though it's the same as the 2022, has somehow encrypted and blocked us from accessing what the autopilot sees. So essentially, 3 months before the test, we realized we might be blind. That means every car could see in front, but couldn't tell us in front. So I think